Hello, my name is Michael Kellner, and I'll present the following joint work of post-quantum Resettably-Sound zero knowledge. This work was done with Mir Bitansky and Shmueli. All of us are from Tel Aviv University, and let's just begin. So I'm going to describe what we're going to talk about in this talk. The first thing we're going to do is to define the notion of quantum resettable soundness. This notion was not defined before our paper, and we'll discuss the definition and why we chose that, and as such. Secondly, we're going to describe in broad overview manner the contributions that we present in the paper. There are three main ones, and we'll discuss them in more detail. Thirdly, we're going to try to give you a little taste of what are the challenges of transforming the proofs from the classical resettable soundness world into the quantum one. What are the technical challenges? Mainly, we'll discuss the case of constructing a quantum resettably sound zero knowledge protocol. And lastly, we're going to discuss some open questions that arise after our paper, and that's about it. So I'm going to start with a little recap on what is zero knowledge. So zero knowledge is an interactive protocol that has three traits. The first two are the common one, completeness, where the protocol actually works, meaning the anonymous interaction between the prover P and the verifier P under an instance in the language X will conduct in an acceptance of the verifier. On the other hand, we would like soundness. In our case, we consider soundness with negligible error. That implies that any malicious prover P star cannot convince the honest verifier of an instance X that is not in language up to negligible probability. And lastly, we require the zero knowledge trait that implies that the verifier, malicious it may be, will not learn any more than the validity of the statement. The way we formalize this is we say that we have a simulator that, given access to the star, some kind of malicious verifier, we can, up to computational indistinguishability, generate a transcript that is indistinguishable than the transcript that B star would have been generated while talking to the real prover P with the witness. Zero knowledge has been a very influential concept in cryptography and computer science as a whole. And as such, and many variants and strengthenings of this notion we consider, the one we're going to talk about this time is called resettable soundness. Resettable soundness is informally the case where we think about a prover that can interact with an a priori fixed verifier across many sessions. What do I mean by a priori fixed? Meaning its randomness was sampled and fixed a priori. So I have some kind of verifier P with randomness S, which is fixed across all the sessions, and a resetting prover that talks about some kind of instance X and try to convince this verifier in one of these sessions. You may wonder what are the motivation behind this security notion, and imagine yourself perhaps a low entropy verifier such as smart cards or virtual machines. So many sessions will have been conducted under the same randomness, even if they resample randomness for every session. But this is not the only reason this notion was considered, but it has a deep connection to what is called black box simulation. A black box simulator implies that the simulator uses the verifier P, the malicious one, in a black box manner, meaning it does not use any of the code or stuff like that, but just queries for the next message and gets the results. And if we have such a simulator that only uses black box access to the verifier, we can easily transform it into a resetting prover by just emulating the rewinding part of the simulator for each rewind by basically conducting a new session and just going the same kind of messages until we reach the point where we want to change the messages and just send the new message and continue on. And because such a simulator can be so seamlessly transformed into a resetting prover, and the simulator needs to somehow cheat the verifier, convince it often true statement, but without the witness, those things, i.e. resettable soundness and black box simulation, cannot coexist together. And indeed, this is shown in the Goldwasser and Lindell from 2001. And using such a view of the world, we can deduce many impossibilities regarding black box simulation. The methodology we imply is that we look at protocols and say, okay, I have, for example, a free message protocol. I can compile it into a free message resettably sound protocol. And if it was black box simulation, then I would have gotten some kind of contradiction against what I already know. So this cannot be done. And indeed, such free message and public constant rounding possibilities and strict polynomial time simulators and possibilities were shown exactly in this manner. And our work will initiate the study of what is called quantum resettable soundness. So the first thing is, what is quantum resettable soundness? And we'll define it more in a bit. But what we allow the attacker is to use quantum attacks against the verifier next message function in order to generate some kind of transcript. We'll define this more formally in a bit. And the motivation we have for doing such a thing is exactly the same. On the one hand, we believe this is a valid security guarantee that we need to consider for adversaries that have low entropy, as was considered in CCA security or in signatures. But also we would like to understand more about what is possible or impossible in regards to post-quantum black box zero knowledge. This is indeed what we hope that the definition and will achieve. So we're now ready to define what is quantum resettable soundness. And to discuss this, let us first begin with the original notion, which is a resetting prover that conducts many sessions with the same verifier and the same randomness. And to transform this into the quantum realm, the first thing we're going to do is give the resetting prover quantum power. However, we believe that this is not enough. Why is that? As you can see here, the resetting prover, although quantum, conducts its interaction with the verifier only by classical means, i.e. cannot, for example, query in superposition on all the first messages in the world. And when considering use cases such as this, and for example, signatures or CCA security, it is more common to consider the case where the resetting prover has quantum oracle access to the verifier next message function. And this is indeed what we decided to do for two reasons. One is which I'll discuss in a bit. And indeed, we give the resetting prover an oracle access to the verifier next message function. And it has, of course, quantum power. It can receive quantum advice. And its goal is to output some kind of accepting transcript. And this is our definition. We have chosen this, one, because we believe this is a valid security guarantee, as I just mentioned, but also because this is the definition that captures the true power of the post-quantum simulator, black box simulator. And as such, we hope that this definition will help us transform the proofs into the quantum world. I do like to mention that there is one variant we might consider, and this is found in literature, is that in our definition, the instance X is fixed, i.e. the resetting prover must prove this specific instance and not just any instance. There are places where they consider multi-instance, where we get a verifier next message function for any instance we choose. And we show in the paper that given a protocol that is secure against a single instance, we can transform it into a protocol that is secure for multi-instance. And that's it. So now that we have covered the definition, we can discuss the contribution that we show in the paper. So the first contribution is a lower bound. We show that any post-quantum zero protocol, zero knowledge protocol that is free message or constant round public coin cannot exist, except for languages that are in BQP. What do I mean by that? We must always remember that any protocol that for a language in BQP can be even zero message, since the verifier can just decide on its own, and as such, it must exist. But for any language that is not trivial, meaning not in BQP, there cannot be a protocol for free message or constant round public coin. I do want to note here that the classical lower bounds that we discussed before does not extend as is, since now the simulator has quantum power. And as we can see and we discuss in the paper, the proof do not work as is, and they require new techniques from the quantum realm of measuring and reprogramming in order to make the original proof. And indeed, we use the original compiler to work. I do like to mention a previous work by Jian et al. That shows the impossibility of black box zero knowledge proofs in the case of free message or constant round public coin, but these exist only, their proof only holds for proof, meaning the prover is inefficient, and indeed the reduction is inefficient, while ours holds for arguments and for proof as well. I would like to give you a little taste of how do we do this. So the first thing we do is we observe that indeed, as in the classical case, if a language has post-quantum black box zero knowledge and resettable soundness in the same protocol, then the language must be trivial, i.e. it is in BQP. As in the classical case, we say that post-quantum black box zero knowledge and resettable soundness cannot coexist together. And using this observation, we apply the same methodology as before and transform, in this case, free message and constant round public coin protocols into resettably-sound ones. And this is indeed what we do in this part of the paper. Our second result is a positive one, where we show that we can construct a post-quantum resettably-sound zero-knowledge argument for NP. Our protocol assumes the hardness of quantum non-trivial errors and quantum fully morphic encryption. The construction is constant round, and I do like to emphasize that zero knowledge in this case is post-quantum, meaning it holds with regards to quantum verifiers, which brings all new things to deal with on their own. And this is indeed a separation between black box and non-black box zero knowledge. Why? Because as we stated before, such a protocol for NP cannot exist in the black box manner, or NP will be in the QP, and a lot of bad stuff will happen. And we'll discuss more how do we construct this in a bit. Our last result concerns what is called virtual black box obfuscation in the case of quantum. And I'll do a small recap on what it is virtual black box obfuscation in the quantum case. So we have the following syntax. We have an operation O that inputs a functionality F and outputs a quantum state law. And we have an operation J that, given an input X and the obfuscated state law, outputs the value of F on X. This is the functionality. This succeeds with overwhelming probability. And what we need to consider is what is the security guarantee we would like to require about this law. And in our case, we consider virtual black box security, meaning that given access to this obfuscated state law is indistinguishable from access to the oracle that implements the functionality F. And in our case, we're going to show a possibility result. So what we want to do is to construct some kind of function family that, given its obfuscation law, we can learn some kind of secret, while given black box access to this family, we cannot. I do like to emphasize the possibilities that that are known in the classical case do not hold in this domain, since we now consider obfuscation using quantum states and not circuits. And as such, quantum states are not copyable and are not and are disturbed by measurements. And these kind of traits prevent us from using the same proofs that were done in the classical case. And indeed, a line of work recently in 2020 showed that this kind of notion is impossible under some assumptions, which we'll discuss more. And we show a complementary result that shows a connection between resettable soundness and quantum virtual black box obfuscation. What we show is that if there is a post-quantum resettably-sound zero-knowledge argument for NP, there's some kind of post-quantum hardness that implies one-way functions, then quantum virtual black box obfuscation is impossible. This result is an analog of the classical result by Bitansky and Kellner from 2015. And using this result in the construction we have just discussed, we can deduce that this is an alternative proof to show that it is indeed impossible to construct quantum virtual black box obfuscation. And our result has similar assumption as the result that are known from 2020, which are cited here. And also, if we were ever to construct a weaker assumption protocol that is resettably-sound and zero knowledge, then immediately we will get a better construction for unobfuscatable function using this connection. So this covers the results that we have proved in the paper. And now I'd like to give you a little taste of what are the challenges of proving these results. And we will start by discussing the protocol that we construct as the second result I've discussed. And indeed, our protocol starting point is the constant round the post-quantum zero knowledge protocol by Bitansky Shmueli from 2020. And the protocol, if I were to describe it in a very informal manner, has two phases. The first phase is where the verifier commits to the challenge it is going to send in the second phase. And the second phase is just a standard Sigma protocol that the prover proves the statement to the verifier. And the main machinery that is done in the protocol is how to extract the witness to the commitment beta while the verifier can be quantum. But if we look at this in the perspective of quantum resettable soundness, we can see that the protocol is not resettably sound even classically. The prover can just run the protocol once, extract the challenge beta, and then conduct a new session. Now he knows better. You can use the standard Sigma protocol simulator to simulate a valid transcript, and it is done. So we need to first think about how we transform it to a classical Resettably-Sound, and then just discuss how do we do this maybe quantumly. So the way this is done in the classical world is the use of the Fiegler-Pilot-Shamil paradigm that has the following stages. The first stage, the verifier sets a trapdoor statement T, and the second stage, the prover has to prove that either T or X is true using a witness indistinguishability argument. And the way that this paradigm achieves the wanted traits is that the trapdoor statement T is indistinguishable from a false one. And during the analysis of the soundness, we gradually transform the trapdoor into a false one and then rely on the soundness of the WI in order to show that X must be true. On the other hand, where we want to simulate, we use the code of the verifier to extract some kind of witness to the trapdoor statement T. And using this, we can prove now with the WI and the witness for T that the statement is true. And since it is WI, this is indistinguishable from the using a witness for X. So this works in the classical realm, but however, we need in our case that the trapdoor statement will be quantum resettably sound extractable trapdoor. What do I mean? It should be quantumly extractable, which is a very difficult thing to achieve. And this was done in the Bitansky Shmueli 20, and we use the same thing, follows that along the same lines. And this is how we show zero knowledge. However, we need resettable soundness for the trapdoor. What do I mean by that? We need the trapdoor to remain indistinguishable, even if we give the prover resetting access to the trapdoor generation mechanism. In order to show the complexity of this, we'll look at a toy example. Imagine that we have a protocol in which the verifier, the prover, sends some kind of message X, and the verifier answers with an encryption of X. So, and the way we show soundness is that we replace the X under the encryption to some kind of other message. And since the prover does not know that we have changed it, since it's under the encryption, we can continue on with our soundness argument. So imagine we have a classical world, which is described in the upper part of the slide. And we have our resetting prover that sends two messages, X1 and X2, and receives their encryptions in independent sessions. Then we can look at a world where we change the value of the under the encryption for one of them, and it is indistinguishable from the other one. And we can do this gradually, one step at a time, using many hybrids, and get to a point where under all the encryptions we have none of the inputs that the resetting prover has sent, and then we can just rely on the original soundness. And since we have only polynomial many sessions that the resetting prover conducts, this will hold. However, let us look at the resetting prover in the quantum case. Although it is efficient, it is not cannot query exponential many times. It can query in superposition, and as such, imagine that it queries all the X's as its first query in superposition. So, do we have now to change all of the encryptions under all of the values under? So we need to change it exponentially many times, but we cannot, since the hybrid argument will not hold. Or maybe we don't need to change, since the resetting prover does not know any of the values yet, since it is even superposition of all the values. This is exactly the question that we need to deal with, also in the impossibility parts and also in the construction part. And we use measurement program techniques that were shown in previous papers in order to prove that indeed all of these constructions and impossibilities and reductions are valid. And I will not be able to get into more details, but I recommend that whoever is interested will look at the full paper and maybe get the details he wants there, he or she. So I'm going to use the time left to discuss open questions that are left after our paper. And I think the first open question that one should consider, if we've shown it is impossible to do free methods, constant round, public coin, zero knowledge with black box simulation, and we know by watchers that almost constant round, small omega of 1 round is possible with public coin, then all that is left is the gap, whether or not constant round without public coin, with private coins exists. And indeed, this was open after a paper for a very, very short time. And subsequent work by Chia et al. Showed that it is impossible to do such a thing. The way they have shown it is they use the same techniques of weather-learning program that we use to extend the result by Barak and Lindell that show that strict polynomial time black box simulation is impossible. On unrelated note, they also show that free message and public coin impossibility holds also for epsilon zero knowledge and not just zero knowledge, which is a weaker notion of zero knowledge. And their novelty in the technical aspect is that they also managed to rule out, using a new technique that is based solely on quantum and specifically quantum entanglement, the expected polynomial time black box simulators are also impossible in the quantum case. And this is only for the quantum cases. In the classical case, this kind of protocol does exist. So this is an important question that was left open for a very short time. Other questions that have remained open after our paper is whether or not the lower bounds hold in the case of quantum communication. Our paper and the Chia et al. Paper both assume classical communication and use the measure and program techniques that assume some kind of classical value. However, if we were to consider a quantum protocol, this will not be the case. And all our techniques will not hold and all the impossibilities. And this is a very interesting question, whether or not we can, this lower bound holds, or maybe we can construct such an object. And the second question that one should ask after the paper is about the connection between obfuscation and resettable soundness. Classically, there is an opposite obfuscation, opposite connection, meaning if we have some kind of unobfuscatable function family, we can construct a resettable sound protocol. However, it's not exactly an unobfuscatable function family, but something called a verifiable robust unobfuscatable family, which has some kind of error correction and verification traits that are hard to construct in the quantum case, since they require some kind of amplification, which will require some kind of measurement in order to achieve, and we cannot do that sort of thing. An interesting question whether or not we can show the reverse connection also in the quantum case using new techniques. So that's it, and thank you very much for listening.